good afternoon. Mr. Fugit here. In our video today, we're going to be looking at group problem 6b, which covers over some of the ideas of work and energy as they relate to a scenario involving a car during a crash test. As always, copies of the group problem are available on Canvas in their respective page. You're also welcome to find the keys there as well. If you have any questions, again, you're always welcome to ask me as well in class when we have time. But here we're going to be looking at how to set up and solve group problem 6b involving work and energy. So, the context of group problem 6b is that you are acting as a design engineer, and you're going to be trying to determine if certain types of cars are deemed safe based on the amount of G-force they allow their passengers to experience. So for each of the four different cars, you're given a value of the initial velocity of the car, the mass of the car, as well as the front end crumple zone of the car. Now in our video, we're going to be working through one of these examples. The reason we're going to do just one is that after we've worked through one, the process for the remaining cars will follow exactly the same as what we do here. So here we're given some information for our first car. We're going to look at specifically car number 1. Now in this scenario, we're told that car 1 has an initial velocity of 20 meters per second. Car 1 does hit the wall and momentarily stop before, ideally would probably hit the wall and maybe recoil back a little bit depending on the collision involved here. But we will assume the car does come to a stop, at least for a brief period of time. We're also told the mass of car 1, 1,100 kilograms. And we're also told the crumple zone of the car. I'm going to refer to this as a delta X because it does describe how much the car is kind of crunched or crumples in as it hits the wall. And we're told the car crumples in approximately 0.8 meters. So the beginning part of our problem asks us to find the change in energy of the car. Now, if we assume we're here on the Earth, we're probably on flat ground as we're conducting this test, the energy that we're probably going to be looking at here is kinetic energy. Right? We start with some velocity in our car, which would mean we would have some kinetic energy, and we likely end with no kinetic energy because we have a no velocity once we've hit the wall and stopped. So part A, we want to find the change in energy of the car. So change in energy would be energy final, how much energy we end with, minus energy initial. Now, our energy final would be 0 meters per second. Well, not our energy final, excuse me. Our energy final, we're really just looking at kinetic energy here, so I'm going to put this in context. Our change in energy, we're really looking at the kinetic energy final minus the kinetic energy initial. Now, the kinetic energy final here would be 0, because our car is hitting its wall and coming to a stop. So now we just need to find the initial kinetic energy, which we can find based on the mass and velocity of our car. So our kinetic energy initially, 1/2 mv squared, 1/2 multiplied by our mass, 1,100 kilograms, multiplied by our velocity, 20 meters per second, squared. Now, as I mentioned, if you're attempting to do this for another car, we would simply use the other car's velocity and respective mass. So here we go, 0.5 multiplied by 1,100, multiplied by 20 squared, we get 220,000 joules. That is the amount of kinetic energy we begin with in this scenario. Now, to find the change, well, we know that the change is equal to our final minus our initial. If our final is 0, that means our change in energy here would be 0 minus 220,000 joules, which mathematically would give us a result of negative 220,000 joules. Now, as we've talked about, work is in fact a scalar value, meaning, energy is a scalar value, meaning energy cannot be positive or negative. But here, we're not necessarily looking at the energy of the car at one point in time, we're looking at how the energy changes. So our result here being negative simply means our object, the car, loses energy, which does seem to make sense, right? Car's moving, hits the wall, it's going to lose some energy in that collision. Right now, in the context of this problem, we're not terribly concerned with where that energy goes. We're focusing more on what's going on with the car. Now, the next part of our problem, I believe, asks us to look at the sign of our change in energy. Should it be positive? Should it be negative? Remember, as we just mentioned, energy itself is a scalar, but changes in energy can be positive, meaning our object gains energy, or negative, meaning our object loses energy. And here, our sign for delta E should be negative. Now next, this will kind of move us into part C. Part C wants us to look at the connection of work and changes in energy. Now, as we've talked about in the context of our course, is that work done on an object equals the change in energy of that object. So once we know the change in energy, we should also know the work being done. So here, using our answer from the first part, we can now determine that the work done on our car is negative 220,000 joules. Now, the other way we've described work is that work is the result of a force acting on an object over a certain displacement, while also factoring in the direction of the force and the displacement, cosine of the angle between those two vectors. So here, because our object is losing energy, there has to be some force causing the object to lose energy. It's likely not going to just randomly begin to lose energy unless some force is acting on it or doing work on it. So now that we have an idea of the work being done, we need to see if we can get to the forces involved. Because the way that we're going to determine if our car is safe or unsafe is to determine g-force, which means we need an acceleration. So we now have work done. We're going to try to use this work value to find a force and then ultimately use that to find an acceleration. So now that we have the work done, let's look at our other equation for work. Now before we do that, part D wants us to draw a free body diagram just so we can get an idea of the forces acting on the car. So let's assume our car is moving this direction into the wall over here. Now, as the car is moving into the wall, there is still going to be a force of gravity from the earth acting onto the car. The car, we can assume, is in contact with the ground. And then as the car hits the wall, at that moment in time, the wall is going to apply a force back onto the car. I'm going to label this normal force upward, F in ground, meaning it's a normal force from the ground onto the car. I'm going to label this normal force F in wall to show that this is the force from the wall onto the car. Now, depending on how you might draw your free body diagram or the context around the problem, maybe we could say that the car was braking, and so there would be some friction going into our free body diagram. Maybe you would want to design this for a car that's accelerating, so there would be a thrust force going forward. However, the context of our problem is such that we're not really told if the driver's braking or if the driver is accelerating. So it's likely that we can assume the car is moving at a constant speed. We're told nothing about the speed changing. So, of the forces that are acting on our car, we need to ask which force is likely going to be the force doing the work, taking energy away from our car. Now, gravity and our normal force, because those forces are not in the direction of motion, they're in the y direction, our car is moving in the x direction, it's likely that those forces aren't going to do any work. Think about our work equation that we dealt with. Work done on an object is equal to the force acting on an object, the displacement of the object, and cosine of the angle between those vectors. If we were looking at the direction of motion of our car, let's say delta x is to the right, it's moving into the wall, normal force and the force of gravity are at a 90-degree angle to the x direction, which means cosine of 90 would be 0, so those forces mathematically cannot do any work on our car. So that tells us the normal force from the wall onto the car is likely going to be the force that we focus our attention on. So this will now move us into part E. Now that we've discussed a bit of what the force is that's really doing the work, the normal force from the wall onto the car, we can then move into part F. Part F of the group problem wants us to take our work value, as well as the displacement of the car, its crumple zone, to try and find the force involved. So here we go, work done on our object. I'm going to call this the work done by the normal force, is equal to the value of the normal force. Remember, we're looking at the normal force from the wall onto the car. delta x, the displacement of the object while the force is acting, and cosine of the angle between those vectors. Now we already know the work being done. We solved for this a moment ago, negative 220,000 joules. The wall takes away all the energy of the car. Specifically here we're talking about kinetic energy. The wall takes away all of the car's kinetic energy because the car comes to a momentary stop. Now the force we're not sure about, so I'll leave this just as Fn. Delta x, that's going to be how far our car moves while it's hitting the wall. That would be the length of our crumple zone, which for car 1 was 0.8 meters. Now the angle between these two vectors, the force and the displacement. Think about what's going on in our scenario. The car is moving into the wall. The wall is pushing back on the car. What is the angle between those two vectors? From 0 to 180, the angle between those would be 180 degrees. So now I'll plug in cosine of 180. I know, just based on the fact that we've done this a few times, that's going to be a value of negative 1. So I'm going to take negative 220,000. I'm going to divide by negative 1. That will get rid of the negative 1 on this side of my equation. I'm also going to divide by 0.8. 0.8. So negative 1 times 0.8, that will give me negative 0.8. So we'll take negative 220,000 divided by negative 0.8, and we get a value for our normal force. Technically, this would be an absolute value of 275,000 newtons. So now we have the force from the wall acting onto the car, which is the force causing our car to slow down. At this point, the next part of the problem wants us to solve for the acceleration of the car. Because remember, acceleration is what we need to find g-force. G-force isn't an actual force the way we understand other types of pushes and pulls on an object. G-force is a ratio of accelerations. So here, this would be in part G. We want to use that force to find an acceleration, which means we'll likely have to look at Newton's second law. Now, coming back to our free body diagram, if we assume that the force from the wall onto the car, the contact force here, is the only force in the x direction, then when we sum up our forces, 275,000 newtons, this is the only force in the x direction. Now, technically that force is to the left. Traditionally, we define in our course that to the left is the negative x direction. We're not really concerned with whether the force here is positive or negative. We just more so want to find what's the g-force. We're not as concerned with the direction. If we want to get technical here, we could define left as positive if we wanted to, but we don't actually have to get into that much detail for the context of what we're doing here. Now, to finish this out, we also know the mass of car 1 is 1,100 kilograms, and we're trying to find an acceleration. So, we'll divide by 1,100 kilograms on both sides of our equation. So 275,000, we'll divide now by 1,100. We get a value of 250. Now, that's going to seem like an extremely high acceleration. Remember, this is describing a car that's going from roughly about 45 to 50 miles an hour down to 0 miles an hour in a very, very short span of time. So even though that acceleration value might seem really high, it's because our car is undergoing a very, very abrupt stop, a very high change in velocity in a very short time. Now lastly, we want to find the g-force on the passenger. Assuming the passenger has the same acceleration as the car, he's a part of the car, they're in system. The last thing we would do here is find our g-force, which is a ratio of the acceleration of our object divided by acceleration due to gravity. Now we've used g-force more so in the context of circular motion, but we can still look at the g-force on an object that's moving in a straight line. So here we go, 250 meters per second squared. Sorry, this is an acceleration, so I should have meters per second squared here. Divided by 9.81 meters per second squared. So now I will divide 250 by 9.81, and I get a value for my g-force of about 25.48. So around 25.5 Gs. Now, that value for g-force is also going to seem reasonably large. But remember, when we're dealing with the context of something like a car hitting a wall, that's going to occur for a pretty short amount of time. And the human body can actually experience this amount of g-force in a very short amount of time, and still reasonably considered to be, considered somewhat safe. Now again, that's not something we would want to continually subject people to, but this is not a certain amount of g-force that a person's going to be experiencing for 10, 20, 30 seconds, right? This would be something that would occur in maybe a half a second to a second. So now we have an idea of what's going on with the g-force on car 1. According to the problem, we're trying to design these cars to have a g-force of less than 40 Gs. Here we are under that value, so we can go ahead and say car 1 will be considered to be safe. So for the other cars that are remaining, the process would be pretty much the same, looking at the change in energy, setting that equal to our work done, using work to find our force, using force to find our acceleration with Newton's second law, and then finally using our acceleration to find g-force. Hopefully this helps you get more comfortable with working through kind of a multi-step problem here. Something that involves a lot of different concepts that we've covered. Right? Things with forces, things with, we could even do this with kinematics because we have an acceleration involved, things with work and energy, putting a lot of these ideas from really the entire year all together in the context of one problem. As always, don't hesitate to ask if you have questions, and remember there are keys available on Canvas if you need access to those. Best of luck.